Welcome to this lecture on surface maps, or maps between surfaces. My name is Marcel Campen from Osnabrück University in Germany.
And I am Patrick Schmidt from RWTH Aachen University.
And we are going to guide you through this exciting part of this year's SGP Graduate School. So our topic for the next 90 minutes are maps between surfaces. What is this about? What kind of maps are we talking about? And why do we care about this? Well, mathematically speaking, maps are functions that essentially describe a correspondence between points from two sets, or domains. Here we are interested in surface maps, that is, maps for which at least one of these two sets is a surface. Concretely, we are going to look into surface-to-plane maps, functions that map a surface into the plane, and, with a particular focus, into surface-to-surface maps, functions mapping between two surfaces.
The case of surface-to-plane maps is quite a bit simpler. We consider this case because it is one important ingredient to surface-to-surface maps. But maps to the plane are also very useful on their own. For example, here we see a surface mapped to the plane, and this map is then used to apply a texture to the object. And that's probably the most intuitive and best known use case of such maps. But besides this and many other visual use cases, such maps are also often used as a computational tool under the hood. For instance, in state-of-the-art quad mesh generation. Such methods rely on suitably constructed maps to the plane and then use these maps to pull a regular grid back to the surface, where it induces a high-quality mesh structure.
Indeed, but our focus will be on surface-to-surface maps, or maps between surfaces. Such maps find use in a variety of computational scenarios where data needs to be transferred or exchanged between 3D objects. An example is texture transfer. So we have, with a lot of effort, created some nice texture on some model, and we want to reuse it on further models. Using a map, we can simply copy it or swap it. Granted, this example here is maybe not of practical relevance, but you get the idea. And besides textures, of course, also other surface signals like normal fields or bump maps can be transferred in the same manner.
Right, and also if some deformation or some animation sequence has been designed for one model, possibly with a lot of manual labor or expensive technical equipment, then a suitable map can be used to transfer this to further models. The same goes for other things that have been designed once with a lot of effort, like particularly structured tessellations that we want to use for multiple models, or patch layouts, here generated manually on one surface and then transferred to another, or an abstract layout to be embedded into multiple target surfaces, or particular templates with semantic annotations, and so on. So by using good surface-to-surface maps, one may be able to fully or partially reuse work that has been done on one model, or maybe even apply it to multiple models right away.
And there are other use cases where the main goal is not to maybe save time, save effort, but where surface maps are actually key ingredients. One example is expressing correspondences between shapes in shape collections, in larger data sets of different instances from one class of objects. For example, there are machine learning applications where training occurs on such geometric data sets that exploit this correspondence information. Also, co-analysis or co-processing algorithms that benefit from simultaneously operating on a set of models in a compatible manner, they need such correspondence information. They need maps between the object surfaces. Examples are co-segmentation of objects or co-remeshing.
And one last example. Interpolating between shapes also requires a surface map. This is, for example, used in morphing applications, either for an artistic purpose or for problems like temporal upsampling, where the state of a dynamic object is only known at certain keyframes, and we want to interpolate between these. But we can only do this if we know which point in one keyframe corresponds to which point in the next keyframe.
Alright, so quite obviously there's a large number of application scenarios that involve maps, in particular maps between surfaces. In a sense, they are a pretty fundamental ingredient and low-level tool in the overall geometry processing toolbox. And in this lecture, we will explore this aspect in the following manner. First, in Chapter 1, we will take a look at how we can actually digitally represent maps. How can we represent them such that they can algorithmically be used and manipulated? It turns out that there is not the one ultimate solution, but a variety of representations are employed in research as well as in practice with different upsides and downsides.
And once this is settled, we will then explore how surface maps can actually be generated and optimized computationally. We will do this in 2 steps. In Chapter 2, we'll see how initial maps between given surfaces can be constructed, such that they reliably and by construction satisfy some hard requirements. We will call this step map initialization. Then, in Chapter 3, we will look into the problem of optimizing surface maps with respect to further soft objectives, such as smoothness, low distortion, and so on.
And we will see that this distinction between initialization and optimization is particularly beneficial when maps are demanded that more specifically are so-called homeomorphisms. That is, maps that describe a correspondence that is continuous and bijective. Now we will see this in more detail in a bit. And this very strict notion of a map is most valuable and will be our focus in this lecture, but we will also touch on other more relaxed types of map definition. For an additional perspective and a more in-depth treatment of such other types of maps, we can recommend taking a look at some lectures from previous years, such as those listed here. But now let's jump right into Chapter 1, Representing Maps. Before considering the case of a map between 2 surfaces, let's start by looking at the somewhat simpler case of a map from the plane to the plane. It is of course closely related, but we can forget about curvature, embeddings, or topology for a moment. So we have the 2D Euclidean plane, or a bounded region in it, omega. A plane-to-plane map F then takes points from this domain and maps them again to the plane, possibly to some other region of the plane, F of omega. An example of such a map would be this one here, which in this case can be quite compactly represented analytically in this form. Such a map can have various properties that will be relevant in the following. First of all, continuity of the map is a common assumption. It is so important that it is quite often even assumed implicitly and not even mentioned. It almost goes without saying. Intuitively, of course, continuity means that something like this here, the domain essentially being torn apart under the map, does not occur. Then there is injectivity. In more detail, we can distinguish between local and global injectivity. A map is locally injective if around each point in the domain there is some neighborhood, maybe tiny, on which the map acts injectively. That is, no 2 points are mapped to the same location. Or in other words, there are no foldovers. The local neighborhood is not folded onto itself when the map is applied. Now, a map is globally injective if this holds not just for local neighborhoods, but for the entire domain as a whole. One then also says the map is bijective, in which case one explicitly or implicitly assumes that the target domain is not meant to be the entire plane, but just the region actually covered by the image of the source domain, F of omega. An interesting observation is that a map that is locally injective is also globally injective if and only if it is injective on the boundary of the domain. Intuitively, if the image of the boundary curve is a simple curve without self-intersections. Finally, a map that is both continuous and bijective is also formally called a homeomorphism. This class of maps, in a sense, is most valuable from the point of view of many applications and use cases, so we will encounter this term quite a few times in the following. But back to the question of how to actually represent the map. In the earlier example, we have described the map analytically using a closed-form parametric expression. That has its limitations, as it can get quite cumbersome when we want to represent more complicated maps with more variation. Then we would need much higher degrees, things would get challenging numerically, and so on and so forth.
And that's why one often works with piecewise linear maps instead of arbitrarily smooth maps. In this piecewise linear case, we assume that the domain is partitioned into triangular pieces. So we're dealing with a triangle mesh here. and our maps are linear or actually affine transformations per triangle. Now for any point in a triangle, here given in barycentric coordinates, its image is already well defined when we know the images of the 3 triangle corners. So to represent such a map, it is enough to simply store the 2D coordinates, also called UV coordinates, of each triangle corner. And that properly and fully defines the map. Now, how do the properties continuity, injectivity, and bijectivity that we talked about translate into this setting? Well, the map could only be discontinuous across edges, so between linear pieces. To restrict to the space of continuous maps, we simply need to ensure that all triangle corners belonging to the same vertex are mapped to the same point. So we just store coordinates per vertex instead of per corner, and that already bakes in continuity into our representation. Regarding local injectivity, to create a foldover that's a locally non-injective situation, there needs to be at least one triangle that flips, meaning that it reverses its orientation under the map. And we can easily detect that by looking at the signed area of the mapped triangle. And this has to be strictly positive. To be very precise, one may also need to include one more condition to exclude non-injectivity at inner vertices. So here the angles around each inner vertex need to sum up to 2 pi, and not, for example, to 4 pi like we see here. Sometimes in a discrete piecewise linear setting, this extra condition is overlooked, because depending on the use case, it may or may not be so relevant in practice. But it is necessary to correctly define local injectivity. Finally, the map is also globally injective if, in addition, the boundary image doesn't intersect itself. And in the piecewise linear case, this boundary is just one big polygon. So with this, we're now already able to represent a homeomorphism in the plane-to-plane scenario. But of course, our focus is on surface-to-surface maps, and we will get there step by step, considering surface-to-plane maps next.
So, if our domain is not a region of the plane, but a surface, how can we deal with that? Well, in what we just saw, we never actually exploited the fact that the domain mesh was lying in the plane. It may as well have been a surface, for instance embedded in R3. More precisely, we now assume our source domain is a triangle mesh A, whether embedded in R2, in R3, or not equipped with coordinates at all, just specified intrinsically by means of edge length. And this mesh is assumed to be 2-manifold, possibly with boundary. Then we can use exactly the map representation we used before, specifying the UV coordinates per vertex. Note that we can interpolate these over the interior of the triangles locally, for instance as formulated here using barycentric coordinates. Therefore, we don't rely on any kind of global coordinate system, which would imply that we would need to do something different here compared to the plane-to-plane case. What, however, does get more complicated in this surface-to-plane setting is the following. While in the plane-to-plane case the source domain inevitably is of disk topology, possibly with holes, a surface can be topologically more complex. Why does this complicate things? Well, if our surface, for instance, is a sphere, there is no homeomorphism, no continuous injective map from the sphere to the plane. It doesn't match topologically. However, every surface can always be cut such that it becomes topologically simple, and then this cut surface can be mapped to the plane. Note that this effectively means that we allow discontinuities in the map, not arbitrarily, but in certain places across a network of cut paths on the surface. More precisely, we can always cut a surface of whatever topology to a set of patches that each have disk topology. It doesn't have to be multiple patches. A surface can always be cut into a single, self-adjacent patch of disk topology, possibly with holes. And the set of cuts that is used for this is commonly referred to as cut graph. Now, when then mapping this patch to the plane, the map inevitably is discontinuous across the cut graph. There's just no way to avoid this in general. Depending on the application, this, however, may not matter much. One example is map-based quad meshing of surfaces, which is a state-of-the-art technique that has been developed extensively over the past 10 or so years. Yeah? The idea is to map a cut surface to the plane and then pull a uniform grid from the plane back onto the surface through the map. While again the map is discontinuous at the cut graph, it can be chosen such that it is in a sense pseudo-continuous. Namely, for this use case, it is sufficient that the implied grid is continuous. The concrete absolute UV values and their discontinuities do not play a role here. Alright, so going from the discrete piecewise linear plane-to-plane setting to the discrete piecewise linear surface-to-plane setting apparently is easy, as we have just seen, yeah? Except for the potential cut-related challenges. Now, let's move to the surface-to-surface case that we are actually most interested in.
Let's start in the smooth setting for a moment before moving to the computationally more relevant piecewise linear case again. So now we're given two surfaces, A and B, both two-manifold, possibly with boundary, and we would like to represent a map F from A to B. If the map is bijective, then we can of course invert it, so then we have a two-way map between A and B. Of course, such a homeomorphism can only exist if A and B are topologically identical, so they have the same number of handles and boundaries. Now, how can we represent such a map? We could try to extend what we saw earlier in the smooth plane-to-plane setting, that is, describe a function from R3 to R3. Now, maybe one that's only defined for those points of R3 that are actually occupied by the surface of A. But the big problem is the requirement that the image of surface A under this map must be exactly on surface B. So essentially we have a constraint that for each point P of A, its image F of P must be on the target surface B. Dealing with such constraints in a setting where maps are to be modified or to be optimized is not that easy. One way to work around this is to exploit the fact that the surfaces are two-manifold, so they can, at least locally, be equipped with 2D coordinates. In this way, we can avoid the constraints that would come with an extrinsic R3-based representation. So equipping a surface with 2D coordinates, that actually corresponds to the surface-to-plane mapping problem that we talked about a minute ago. Because such a map essentially pulls the 2D Euclidean coordinate system from the plane onto the surface. And that's why such a mapping to the plane is also commonly referred to as a parametrization. It equips the surface with UV parameters. When we then define a map between A and B using these 2D coordinates, then we can actually view this as a composition of three maps. A map from A to the plane, a map from the plane to the plane, and another map from the plane to B. Actually, the plane-to-plane map in the middle here is redundant. So we can always choose the surface-to-plane maps such that this map in the middle is the identity, so we can just drop it. Now what we did is we effectively reduced the surface-to-surface mapping problem to the surface-to-plane mapping problem. So that's one option, but an option that's also not without drawbacks either. As we've seen earlier, we have to cut our surfaces to disk topology. And these cuts now somehow need to be compatible, and we need to deal with continuity or transition issues across cuts and so on. Later, we will be able to work around this, but first, let's switch to the discrete piecewise linear setting that we're actually most interested in.
This means our two surfaces A and B are now triangle meshes. Two-manifold, possibly with boundary, and we want to represent a map F from A to B. A simple approach is to follow the extrinsic representation mentioned a moment ago. That is, for each point of A, we store 3D coordinates, x, y, z, giving the image of that point under F. And to make it finite, let's store this info only for each vertex of A. Yeah, we could call this a vertex to ambient space representation. This has been used in some works. It's pretty simple, but it has some obvious shortcomings. In particular, the constraint that the map actually maps onto B is not inherent in this representation. Yeah, one has to separately take care of that, which is possible, but maybe a bit cumbersome. A more elegant approach is to use a representation where this constraint onto B is inherent. This can be achieved with a vertex-to-surface map. Instead of per vertex storing 3D coordinates, we store a point that, by definition, is part of surface B. Concretely, per vertex of A, we can store an arbitrary point inside an arbitrary triangle of B, represented by the triangle's ID and the point's relative position inside that triangle. For instance, based on some local 2D coordinate system, most easily based on barycentric coordinates in that triangle. In this way, the map images lie on surface B by construction. This idea can be restricted further for simplicity. For each vertex of A, we store not an arbitrary point on B, but specifically a vertex of B, referred to simply by its ID. This, of course, limits the flexibility of the map, but due to its simplicity, this kind of representation has also been used quite a bit in lots of research works. In particular, this kind of representation does not use any coordinate values, just combinatorial correspondence information. An even more compact variant of this are so-called functional maps. Here the idea is to not represent individual single vertex to single vertex information, but to represent correspondence in a less sharp manner. Imagine a fuzzy blob on A, and we just say this corresponds to some fuzzy blob on B. If we do this for much fewer blobs than there are vertices, the map representation itself, in a sense, is more compact, but also less sharp. We don't have precise map image information down to the individual vertex. More formally, these blobs are actually discrete functions on the mesh with a scalar value per vertex, hence the name functional map. Most commonly, low-frequency functions are used for that purpose, for instance from a Laplacian eigenbasis of the mesh, truncated at some frequency to compactly represent at least the gist of the map, the global behavior, but to ignore the local detail, which may be an advantage or a disadvantage depending on the application scenario. We will not go into more detail here at this point, but refer to these previous lectures listed here for a broader excursion into this field. A common problem of all these representations, whether vertex to surface, vertex to vertex, function to function, is that they only explicitly state image information for the vertices of A. What about other points of A, on edges, on triangles? Well, on A, we can of course express them as linear combinations of 2 or 3 vertex positions. We could apply the same combinations to these vertices images to extend the map definition to all points, like we did in the piecewise linear plane-to-plane and surface-to-plane setting. This linear interpolation of the images, if done in R3, however, leads to an image that, again, is not confined to surface B in general. So this is not an actual map from A to B. In particular, this map is not bijective, not onto B. It certainly is not a homeomorphism, and we could not invert this map, just to give an example of the shortcomings of such a representation. An idea could be to perform some kind of projection from the ambient space interpolation back onto the surface. And various instances of this idea have been employed in a number of works. However, it must be noted that there is no known way to do this in such a manner that the projection leads to a homeomorphism in general. Depending on how the projection is done, either continuity or injectivity or surjectivity will be violated in general, often even multiple of these properties. The only way to reliably obtain a general definition that enables the proper representation of homeomorphisms is to perform the interpolation somehow within the surface, within the 2-manifold, rather than in 3D ambient space. To this end, we need to have some kind of explicit or implicit, local or global 2D parametrization of the surface, so as to have 2D coordinates available with respect to which the interpolation can be defined.
Earlier we already mentioned that we could use parameterizations for this. So we can overlay the images of both meshes in the plane to define our surface-to-surface map. Now for any point on surface A, no matter if on a vertex, on an edge, or inside a triangle, we can follow the first piecewise linear map into the plane. There we look up which triangle of B we hit, we express the point in a coordinate system of this triangle, for example via barycentric coordinates, and then we follow the second map to mesh B. Now the resulting point lies exactly on the surface, because we performed our interpolation in the 2D plane instead of in 3D ambient space. Now if both maps into the plane are bijective, then the resulting map between the surfaces is also bijective. And we've successfully defined a homeomorphism. Now the simplest case is when both of these surfaces actually have disk topology. So then we just have to decide on how to handle the boundary. One option is to choose a free boundary setting and not even constrain both boundaries to each other. But then the map will only be defined in the overlapping region of both meshes in the plane. For some applications this might be okay or even desirable. Maybe both boundaries aren't even meant to exactly correspond to each other. But if we're interested in a full homeomorphism defined everywhere, then we need to ensure that both boundaries match exactly in the plane. Okay, now how can we map between non-disk topology surfaces? We already saw that not every surface can be bijectively mapped to the plane without cutting. And this poses a major challenge that can be addressed in different ways. We can, for example, first cut both surfaces to disk topology in a compatible way, and more on how to do this will follow in the next chapter. And then we could map via the plane with both boundaries matching each other exactly. Now we have a full homeomorphism, but this fixed boundary correspondence can be very restrictive. For example, it's not easily possible to optimize the map at or across these cuts.
There are various options to work around this and to allow a more flexible handling of cuts. One is via specific tilings of the plane, for example so-called orbifolds, where a surface, after cutting it into disk topology in a specific way, is mapped to a region of the plane. When now a second surface is cut in a similar way and mapped independently, the images, of course, may not overlap perfectly, and we have a problem. This does not define a complete bijection. However, as you may notice, when mapping this to the plane, it was ensured that the boundary has a particular symmetry. And due to the symmetry, we can virtually duplicate it and, after some rotation and translation, glue it to itself. You see, this is really just a rotated copy. And we can do this in such a way that it can cover the entire plane. We could repeat this infinitely. When then overlaying this with the map of the other surface, this defines a complete map between the surfaces, as there now is a complete overlap. No matter how the concrete boundary shapes differ, they just have to obey this symmetry, which can be incorporated in the map construction process. However, such tilings require us to choose certain singularities. These are points lying on the cut, as marked here, around which multiple copies of the same tile can be found. And a certain number of these singularities has to be chosen, and they inevitably dictate a point-to-point correspondence between both surfaces at these points. This is because both tilings of the plane need to follow the same pattern so as to well define a map. Now, the good news is that with this representation, due to the specific type of tiling, the actual shape of the cuts doesn't matter anymore. So we could move a cut around without changing the way our surface lies in the plane. This also means that when overlaying two tilings, their cuts don't have to match each other anymore. So we gain some flexibility at the cuts, but are still limited by the choice of singularities, which are crucial for this construction. And dealing with such singularities is kind of cumbersome and can add additional complexity to the problem.
So finally, let's try and find map representations that work without having to choose singularities. An arbitrary surface cannot be mapped to the plane continuously and injectively without having to choose such special points. And the reason for this is described by the Gauss-Bonnet theorem, here in a simplified version for closed surfaces. It relates the total Gaussian curvature to the genus of a surface. For example, if we integrate the Gaussian curvature over any surface of genus 0, then the result will always be 4 pi. No matter how we deform the surface, its total curvature will never change. The plane, however, is flat. It has 0 curvature everywhere. Now, in the previous orbifold setting, we essentially concentrated all the curvature that we have at a few select points, at the singularities. But if we don't allow singularities, then there's no place we can transport this curvature to. So instead of trying to get rid of the curvature, we could try to distribute it uniformly, such that every point on the surface receives the same amount of Gaussian curvature. And what we'd end up with is a sphere. In fact, every genus 0 surface can be bijectively mapped to the sphere, and we could use the unit sphere as our intermediate domain of choice for maps between genus 0 surfaces. Very similarly to the planar case, we can now compose a map from surface A to the sphere with a map from the sphere to surface B. And this approach has been successfully used in a lot of different works. Next, let's see what happens for genus 1, surfaces of torus topology. Here, the total curvature is in fact 0, so an injective map to the plane is possible without singularities. The result is a tiling of the plane, also called the universal cover, in which again the specific geometry of cuts doesn't matter, and in which individual tiles are now only related by translations, so there are no singularities. And the cuts we use here, they are really just a visualization or implementation aid for us, but they don't need to exist mathematically. And now that we found out that we can map any genus 1 surface to the plane, we can use the same technique and compose 2 or more maps from different surfaces into the plane, as long as they tile the plane via the same pattern. But what happens for genus 2? Luckily, we don't have to continue this case distinction forever, but we can handle all surfaces of genus 2 and higher together. Because for all of these, the total curvature is negative. Now again, let's distribute this curvature evenly over the surface. And constant negative curvature means that the surface locally looks like a saddle at each point. Now it's hard to picture what the overall shape would look like. And the reason for that is that in fact a surface with constant negative curvature cannot be embedded in Euclidean space without distortion. The object we're talking about, a two-dimensional space with constant negative curvature, that is called the hyperbolic plane. To represent points and perform computations in the hyperbolic plane, there are a number of ways to embed it in 2D or 3D Euclidean space, but each of these has a different type of distortion. And these are called models of the hyperbolic plane. One of these is the Poincaré disk model. So here the entire hyperbolic plane is mapped to the open unit disk in 2D. Distortion increases indefinitely towards the boundary of the disk. So if I'd walk in the hyperbolic plane with constant speed, my projection in this model would slow down more and more the further I get to the boundary of the disk, so much that I will never be able to reach it. Geodesics in the hyperbolic plane, these are the equivalent of straight lines in the Euclidean plane, these become circular arcs in this model. Now, very much like for the flat plane earlier, there always is a map from our higher genus object to a tiling of the hyperbolic plane without singularities. Here we show just a single tile in the Poincaré model, and again, using 2 such maps into the hyperbolic plane, we can define a homeomorphism between 2 higher genus surfaces. If we only store the coordinates for a single tile per mesh, like you see here, then of course we need to take care of transition functions across the cuts. But again, the exact choice of these cuts doesn't matter. We could also do the same thing using the Beltrami-Klein model, for example. This is very similar, but it maps geodesics to straight lines instead of circular arcs. The third model that we want to present here is a bit different, as it maps the hyperbolic plane to a surface in 3D space, namely to the upper sheet of a hyperboloid. And this model is called the hyperboloid model, or the Minkowski model. It's interesting because it provides a nice way of computing intersection points between geodesics in a way that also generalizes to the sphere and the Euclidean plane. So geodesics in this model are constructed by taking the plane through 2 points and the origin, and then intersecting this plane with the hyperboloid. This is nice because geodesics on the sphere are constructed in the exact same way, as an intersection of a plane through the origin with the sphere itself. Now, to also make this compatible with the flat 2D plane, we embed the plane in 3D ambient space and lift it slightly so that it no longer contains the origin. And now we can use the exact same construction again to generate straight lines. Now, in all 3 cases, the intersection point with another geodesic can be computed by intersecting both of their defining planes with the respective model manifold. And we will shortly see why computing all these intersections between geodesics is such an important operation. It will also play a role in our last chapter where we talk about map optimization. So, in summary, we've seen that for closed surfaces of any genus, we can compute maps via a constant curvature intermediate domain, that is, via the sphere, the plane, or the hyperbolic plane, depending on the genus. And these representations work without having to choose any singularities in our map.
One interesting observation we should not forget to point out. We have seen that in the case of genus 0 surfaces, they can be mapped to a constant curvature intermediate domain, the sphere, globally, without any need for cutting. For genus larger than 0, that was not possible. Note, however, that locally, any piece of a genus 1 surface can always be mapped to the plane, and any piece of a genus 2 or higher surface can always be mapped to the hyperbolic plane. This leads to the idea of not representing these maps to the intermediate constant curvature domain by means of absolute global coordinates, but relatively. In other words, instead of using a map, we can use a metric. More concretely, instead of equipping vertices with coordinates, we can equip edges with length, which is then referred to as discrete metric. In a sense, we use differential information. And this voids the need for any kind of explicit cuts, transitions across cuts, dealing with infinite tilings, etc. For any piece of a surface, a coordinate embedding can always locally be constructed from this metric information, just as needed by the operations such as geodesic path computation.
In all the different map representations we've shown you so far, we described how to map individual points from surface A to surface B. We represented our maps such that this is possible for every point, so in theory this is all we need to define a proper homeomorphism. But for some applications it might be important to explicitly represent the piecewise linear nature of a map, meaning that we actually break up our map into linear pieces like triangles or polygons, such that then a map can be processed more like a mesh. And this is most straightforward to explain when mapping via the plane. So here we have a map from mesh A to the plane. This is piecewise linear in the triangles of A. We then compose it with another map that is piecewise linear in the triangles of B. Now the composed map is also piecewise linear, but now only in the overlap of a triangle of A with the triangle of B. So to explicitly represent this piecewise linear nature, we intersect the triangulations of A and B in the plane, and that forms the so-called overlay mesh. And for simplicity, we can also triangulate it. Now we can lift the overlay mesh once to surface A and once to surface B. So the map is now represented via a common triangulation of both input surfaces. In other map representations, for example via constant curvature domains, we can follow the same idea. We compute an overlay mesh by intersecting the edges of both meshes, now in the constant curvature domain, that is, on the sphere or in a hyperbolic model. And we then lift the common triangulation to both meshes. And this is why these nice geometric constructions to compute intersection points come in very handy. Now, evaluating such an explicit piecewise linear map is very easy, and it doesn't even require the intermediate domain anymore. We can just express a point via barycentric coordinates in an overlay triangle on A, and then evaluate it again in the other instance of this triangle on B. We can also use this overlay mesh to directly transfer texture coordinates, in particular textures with seams. Because if one of these edges on A is a texture seam, then it is now also explicitly represented in the overlay triangulation of B. If we didn't have this overlay mesh, then, for example, just a vertex to vertex or vertex to surface map, then transferring seams correctly would be pretty difficult. Later in the optimization chapter, we will also use this overlay mesh as the discrete domain to measure map distortion in.
One final remark. Notice that the way of representing a homeomorphism by means of interpolation with respect to some intrinsic coordinates or metric essentially defines the images of A's edges on B in an implicit manner. Which edges of B they cross in which order depends on the metric. The representation via common tessellation we just added instead explicitly represents intersections between edges of A and B, to have all this combinatorial information readily available. So why can't we use such an explicit representation from the start? This essentially comes down to how hard it is to modify such a map, for instance during map optimization. People, including ourselves, have experimented with such approaches, but it turns out that things get pretty messy due to the various special cases that can arise and due to the efforts needed to update all this explicit information and to keep it consistent at all times. The implicit representations that we have talked about make it a lot easier to continuously modify a map. When necessary, it can always be converted into an explicit piecewise linear representation when necessary. For example, to evaluate distortion measures or to provide a simple output format for downstream applications.
Alright, let's summarize what we learned about surface-to-surface map representations. So to faithfully represent a homeomorphism, that is a continuous and bijective map, we need to rely on interpolation in a 2D parametrization. For this, we can use the plane right away in the disk topology and genus 1 case. In all other cases, we first have to cut our surfaces to disks and potentially add singularities at certain points. We can work without singularities if we map genus 0 surfaces via the sphere and genus 2 and higher surfaces via the hyperbolic plane. Maps to this intermediate domain can either be represented via global coordinates or via metrics. And finally, all these map representations can be turned into an explicit, piecewise linear form for easier processing.
Now we know various ways to represent maps, but how to actually get maps, how to obtain maps, how to generate maps in the first place. In some applications, in particular when working with synthetically constructed data, a map may be known naturally due to the way the surfaces are generated. For instance, when different poses of a character are designed by deforming a reference pose, a homeomorphism between these is known inherently and more or less trivially via the mesh connectivity. In other cases, however, we want to computationally construct or find a map between surfaces or from a surface to the plane. And typically, one is not interested in just any map, but a map that is subject to certain soft goals and or hard constraints. For instance, one very common and intuitive goal is that the map is smooth in some sense. Or in other words, that it has low distortion. When mapping some data from surface A to surface B, it should not undergo heavy distortion. How to actually measure distortion, how to quantify it, that's a separate question, and various application-dependent distortion measures are commonly used. We will discuss this in more detail later. Additionally, beyond these purely geometrical questions of map distortion, semantics can be of relevance. Here, just to give an example, we see a map between a cow and a giraffe, or actually parts thereof. It is optimal in that it has, in some particular sense, least distortion among all homeomorphisms between these two surfaces. But semantically, it may not be what one would like to have. For instance, the cow's nose is mapped partly down the giraffe's neck, or its hooves reach almost up to the giraffe's knees. In other words, the map is unaware of these semantic categories. And taking such semantics into account is a highly challenging issue from an algorithmic perspective. In the field of machine learning, there are efforts underway in this direction, but this is beyond our scope here today. We focus on geometric and topological aspects. So, Taking the low distortion perspective again, we find that simply looking for the globally smoothest, least distorted map is not necessarily what one would actually wants or needs. Instead, in applications, we often have certain constraints that are to be respected. For instance, we may know somehow that a particular point on surface A is supposed to be mapped to a particular point on B. If we knew this for all points, we wouldn't be looking for a map anymore. Instead, there are scenarios in which we know this for a sparse set of points, in some cases referred to as landmark correspondences. On the one hand, this can be viewed as complicating the search for a map, as additional conditions are to be satisfied. On the other hand, this correspondence information can also be viewed as actually making life easier. This is because searching the extremely huge space of maps between two surfaces for the globally optimal map is a problem that is rarely feasible in practice. Any kind of given correspondence information or constraints may therefore help us narrowing down this space or starting the search at a position already closer to the desired optimum. We will see this in more detail in a moment. But besides such point constraints, one may also have knowledge about curve correspondences. For instance, for a particular feature curve on surface, we may not know for each and any point on the curve which concrete point on the other surface's curve it should be mapped to, but that it should be mapped onto the curve. Even more generally, one may consider region correspondences. However, point correspondences and therefore point constraints are by far the most commonly available and most commonly used types of constraints. So, to summarize, we would like to find a map that 1. Is bijective and continuous, a homeomorphism, that 2. Respects the given constraints, and 3. Among all maps satisfying this, has least distortion. Theoretically, we could start with some map, any map, that maybe satisfies neither of these 3 conditions, and then run some kind of optimization procedure that aims to achieve all 3. Unfortunately, there is no known method that could guarantee convergence to a state where all 3 are actually simultaneously satisfied in the end. If 3 wasn't satisfied, that is, if the resulting map would not be the ultimately globally least distorted map of them all, we may be able to live with that. So this can be seen as a kind of soft goal. If, however, 1 or 2 are violated, this would mean the map is actually invalid, not a homeomorphism, or not respecting the constraints the application requires. So these 2, by contrast, must be seen as hard constraints. And this distinction has quite naturally led to the following 2-step approach for the computational generation of maps that exhibit the desired properties. In a first step, we construct a map that, by construction, is continuous, bijective, and respects the constraints, while not necessarily caring about distortion at all. So, in other words, let's first worry about the hard constraints. Let's make sure they are fine. And then, in a second step, we can incrementally modify the map, optimize the map, so as to reduce or minimize its distortion, while making sure that the initially established properties, bijective, constraint respecting, are preserved or maintained. So we may say the first step is the initialization of the map, the second step then is the optimization. And these 2 steps we are now going to look into in more detail in the following 2 chapters. In this chapter, our goal is to understand how we can algorithmically construct maps that are bijective and continuous, but that, as we have seen, is pretty straightforward, and that respect certain constraints. And we will focus on the most practically relevant point constraints here. Additionally, for maps between surfaces that are topologically non-trivial, the aspect of map topology plays an important role, and we also need to get that right. Our focus will be on maps that are homeomorphisms and defined for each surface point, as arguing about continuity or bijectivity properties of, for instance, vertex-to-vertex maps is quite futile. One of the key results when it comes to constructing a map that is injective or bijective onto a certain domain is Todd's embedding theorem. given a triangle mesh of disk topology, fix the boundary vertices images to a convex polygon in the plane, preserving their order, then solve a linear system that requires each non-boundary vertex image to be the average of its neighbors. The result is guaranteed to define a piecewise linear map from the surface to the plane that is injective, or that is bijective, onto the chosen convex polygon. Problem solved? Well, we have two major restrictions here: surface to plane setting only and convex domains only. Both restrictions can be lifted, however. We can map a surface A onto an intermediate convex planar domain and the actually desired non-convex domain B onto this intermediate domain as well. To this end, we can triangulate it and then use the same TUT embedding technique. When we then combine the first map with the inverse of the second map, that is invertible due to the guaranteed injectivity, we have a map onto the desired arbitrarily shaped domain. Representing this map is a bit more complicated though. While it is piecewise linear, it is not linear per triangle of A, but linear per intersection of a triangle from A with a triangle from the triangulated target domain. Because it is the overlay of two piecewise linear maps with different triangulations. Notice that the described construction does not actually require that the triangulated domain actually is in the plane. It may just as well be a surface mesh. So using the same idea, we can generate a bijective map between two surfaces A and B. Again, we have the situation that the result is piecewise linear per intersection of two linear pieces, a triangle of A and a triangle of B, which is even more obvious in this surface-to-surface case. And what if the surfaces do not have disk topology? Well, again, we can cut them to disk topology and then establish the map between these two disk patches. While this immediately yields a bijective map, we need to pay extra attention to continuity in this case. It was essentially built in before, but whenever we are cutting, continuity is at risk. And to avoid discontinuities, we need to ensure that 2 points that are identified across the cut on A are mapped to the same point on the cut on B. As we have full control over the map along the boundary, or in this case along the cut, when using TUT's embedding idea, we can very easily ensure this. However, this is only feasible if the cut graphs on A and on B are structurally identical, if they have the same combinatorial graph structure. The probably simplest way to achieve that is to use a cut graph that is a so-called system of loops, a set of loops rooted at a common point. For a genus G surface, we can choose 2G such loops, such that they cut the surface topologically to a single disk patch. When then mapping the cut surface to the plane, for instance, such that the cut along each loop has a straight image, we get a polygon domain like this. This is also referred to as fundamental polygon. Depending on the order in which the loops are cyclically attached to the root point, their order along this domain boundary will differ. So to enable a continuous mapping along the boundary, and therefore a continuous surface-to-surface map, we need to choose this cyclic order around the root point to be the same on surface A and surface B. And there are computational topology algorithms that can easily do that, and then everything works out as expected. As a quick remark, let us point out that TUT's embedding theorem has been around since 1964, and since the mid-1990s and until today, it is in broad use in graphics and geometry processing and beyond. Recently, however, quite some progress has been made regarding an alternative technique to yield injective maps. Instead of TUT's embedding, which can be seen as a form of discrete harmonic mapping, this alternative is based on discrete conformal mapping. In a sense, it is more flexible. It does not require convexity. It does not require fixing the boundary. It supports non-planar domains. On the other hand, it is algorithmically a bit more involved, yeah? But we will see what the future will bring in this context. It's still a pretty novel direction at this point. All right, now we know how to get some map that is bijective, but how to ensure that the map respects prescribed correspondences. So we want that some particular point on A is supposed to map to a particular point on B. Yeah, and we typically want this for a bunch of such points, sometimes also referred to as landmark correspondences. The problem, neither with TUTS embedding nor with the discrete conformal mapping techniques we just mentioned, can we control where points map to specifically. Yeah, if we simply add such a constraint and take the variables out of the systems, we immediately lose our injectivity guarantee. But wait, while we cannot do this for any interior vertex, we can and even must actually prescribe the image of boundary vertices. Therefore, an option is to cut the surface such that afterwards all constraint points lie on the boundary. Yeah, and then we can control their image and prescribe where they map to. And the simplest type of cut would be a spanning tree, yeah, that connects all these landmarks. Alternatively, one could think of an intrinsic triangulation or patch decomposition that has the landmarks as its vertices. Yeah. Of course, similar to the discussion a moment ago, to be able to maintain continuity when cutting in this way, the target domain or target surface needs to be cut in the same way structurally. Yeah, so we are now facing the problem of constructing spanning trees or triangulations on two domains or surfaces in a structurally and topologically compatible manner. And well, this condition can rather easily be incorporated into the incremental construction of a spanning tree. Yeah, paths between pairs of landmarks are added one by one simultaneously on A and B. That is, when a path is added between two landmarks on A path is added between the two corresponding landmarks on B. Yeah? And to ensure compatible cyclic order of path around landmarks, one needs to choose the path on B such that it meets the landmarks in the same sectors. As long as less than two paths have been connected to a landmark so far, there is only one sector to choose from, so no care needs to be taken. But if more than two have been connected, then there are multiple sectors, and then the corresponding sector needs to be picked. And that's how a compatible cut graph can be obtained. One further important aspect is map topology. Generally, when choosing the cut graphs on A and B to handle surfaces of non-disk topology, there are many degrees of freedom. Yeah, some are geometric degrees of freedom, but some are topological. What does that mean? Well, whether I choose a cut like this or like this does not matter fundamentally. Yeah, the constructed maps will be different, but one can be continuously altered or deformed or optimized into the other. Yeah, this is what we will do in the following final chapter on map optimization anyway. So the only difference between these two cuts is that the optimization may have a little more work to do. Whether I choose a cut like this or like this, however, makes a fundamental difference. Yeah, the two maps defined using these two different cut graphs will differ topologically. Yeah, formally, they lie in different equivalence classes of the so-called mapping class group. Yeah, they are different in terms of map homotopy. They cannot be continuously deformed into each other. Any kind of continuous map optimization will not be able to switch between different classes, and therefore it is very relevant which cut graph we choose to initialize the map, because this will once and for all fix certain topological properties of the map, unless we perform major non-continuous modifications later. Yeah, but this is largely unexplored territory in terms of practical algorithms. Yeah. And it is important to note that this is not only relevant for surfaces of higher genus. Yeah, the presence of landmark correspondences or landmark constraints likewise increases the topological complexity of the setting. Yeah, intuitively, the cut graph differs topologically not only when it winds around some handles of the surface in a different way, but already when it winds its way through the landmarks in a different manner. Two maps initialized based on two cut graphs differing in this way cannot be deformed into each other. unless one temporarily sets the landmarks free during deformation or during optimization, but then there is no guarantee that one will be able to ultimately satisfy them again in practice. Yeah, and this all shows that it is crucial to make the right choices at this stage, even on simple genus zero surfaces. How can this be done in practice? Well, as this is a pretty challenging problem, not rarely it is suggested or assumed that these topological decisions are made manually or given as input in some form. Algorithmically, this problem has been approached mostly by greedy strategies, based on the often reasonable but somewhat risky assumption that building the cut graph out of shortest path in some greedy shortest first order leads to the desired result. Very recently, we have started looking into more global and non-greedy ways of making these crucial topological decisions. One option, for instance, is to globally search for the one order of constructing the individual shortest path that form the cut graph that ultimately leads to the least tangled cut graph. In another work, we show how to extract topological information from maps or partial maps, even just landmark correspondences, and to use this information to constrain the cut graph construction, excluding topologically unfit or unreasonable configurations. So there is progress being made in this direction. A lot of things work nicely by now, but there is still a lot of room to gain something here, as this is really a crucial part, as we have seen. To conclude this map initialization chapter, let's talk about shape matching just briefly. We have so far assumed that there are some landmark correspondences that kind of constrain what the initial map will look like to some extent, which will then make it feasible for a subsequent optimization to reach a map that satisfies all desiderata. Where do these landmarks and their correspondence information actually come from? Well, this is certainly application dependent. From a research point of view, the most interesting problem is how such correspondence data can be computed automatically, so that we do not actually need them as input. Of course, this problem may involve semantic aspects and so on, but even if we restrict ourselves to the purely geometric perspective, this problem is already very challenging. Related research works address tasks in this field, such as identifying particular distinctive points on surfaces, for instance, based on shape descriptors, finding matches for such landmark points, globally searching for suitable correspondences, or resorting to rough approximations for feasibility, and so on and so on. But this field of geometric shape matching is a complete research field of its own. We just want to point this out here very briefly before concluding the initialization chapter.
Okay, now that we know how to represent and how to initially construct maps, let's talk about optimizing them for low distortion. We'll start with some intuition, then give practical instructions on how to measure distortion, and finally give a brief intro into continuous second-order optimization. So let's imagine that our surface A is made of some stretchable material, like an elastic glove that we want to fit to surface B via our map. So while this map here looks pretty decent, this one does not. It appears distorted. We can quantify this distortion by looking at how much each little piece of material needs to stretch or shrink when going from A to B. And this is called intrinsic mapping distortion. Here we visualized it as a heat map. Now we want to come up with an algorithm that modifies our map or moves the material around the target surface such that the overall distortion decreases. And this is also called an energy minimization problem, where we call the total amount of distortion an energy and move towards a minimum energy configuration. When speaking about optimization, we also call this energy our objective function that we want to minimize. Here's another example of an initial map. It looks quite smooth overall, but we did not correctly align one of the fingers. So the glove needs to stretch a lot in this place and contract all the extra material over here. So we can see that there is a relation between alignment of geometric features and stretch in our map. And reducing distortion can encourage good alignment. But be aware that minimum stretch doesn't always imply semantically correct alignment. So for a pair of very different shapes, It might not even be clear what correct alignment even means. But for now, we'll simply focus on distortion minimization or stretch minimization, because this is a very well-defined goal. Now, we could also ask whether strictly decreasing distortion will always lead us to the least distorted out of all possible maps. That is, will we reach the global minimum? And sadly, this is not always the case, because usually there are several local minima. For example, here we start with an initial map where the fingers are offset by 1. And strictly decreasing distortion will not get us out of this situation. Because to move towards the global optimum, we'd first have to increase distortion for a while before we can then decrease it again. But we don't even know in which direction the global optimum lies, so we can't really do that. And actually, trying to find the global optimum is very difficult because the space of possible solutions is extremely large. So really, all we can do is sticking to finding a nearby local optimum. And again, this underlines how important it is to start from a good initial map or rely on good input constraints. Okay, now with this bit of intuition in mind, let's look at how to actually measure distortion. So for an infinitesimally small piece of our source surface, we want to know how it gets stretched out on the target. And this information is given by the differential df of our map. At a specific point, it tells us how a tangent vector from the source is mapped to a tangent vector on the target. So it's a linear map between tangent spaces, and we can describe it by a 2x2 matrix called the Jacobian. Now, instead of checking how much a specific tangent vector grows when mapping from A to B, we can compute the directions of minimum and maximum stretch directly via a singular value decomposition of the Jacobian. The singular values themselves give the amount of stretch along these two directions. So ideally, we would like both of them to be 1, meaning that there is no stretch at all. If this is the case at every surface point, then we call such a map an isometry, because it has no intrinsic distortion. But of course, between two different surfaces, such an isometry rarely exists. In our example of mapping between two hands, we might get pretty close to an isometry, but in general, all we can do is trying to find a map that is as isometric as possible. Okay, so many different distortion measures based on these singular values have been proposed. For example, we could look at their product to measure how area is changed by the map. Or we could look at their ratio to see how angles are distorted by the map. One other thing we could do is squaring both singular values, and then a piece of surface wants to shrink indefinitely when going from A to B, because both singular values now want to become 0. And this is called a Dirichlet energy. If we also add a similar term in the other direction, then things also want to shrink going from B to A, and then these two terms have to find some balance. And this is called the symmetric Dirichlet energy, and it's really popular in parameterization and surface mapping. So we can write it using the squared singular values and the squared inverse singular values. There's also an alternative way to write it directly in terms of the map Jacobian. And we can see that this energy is minimized when both singular values are 1. So it is indeed an isometric distortion measure. In the following, we will keep using this energy as our objective function, but keep in mind that other measures based on the map Jacobian can be used as well. Now, no matter which option we chose, what we now have is a pointwise distortion measure. And to measure the overall distortion of the entire map, we need to integrate it over a surface. Which surface we choose as integration domain, that's another choice we have to make. In the surface to plane case, one often integrates over the source surface, because this remains constant throughout the optimization. In the surface to surface case, some literature proposes to integrate both individual Dirichlet terms over their respective target domain. Now, how do we actually compute the symmetric Dirichlet energy in a discrete setting? Let's start with the plane-to-plane case. So here we have two instances of this triangle. They are related by an affine transformation, and the Jacobian is the derivative of this transformation, or just the linear part of the map. Now, to compute it from given vertex positions, we can, for example, look at these two edge vectors and their images, and then just solve for the linear map between them. Now we plug this Jacobian, or its singular values, into our distortion measure and integrate it over the triangle. Since the Jacobian is the same everywhere in the triangle, integration just means multiplying our pointwise measure by the triangle area. And here we chose the area of the source triangle. Now we just do this for all triangles and sum up the results. As mentioned earlier, we need to ensure that we maintain our strict continuity and injectivity criteria during optimization. So continuity is already handled by the way we represent our map, because neighboring triangles share common vertices, so there is no way we could tear our mesh apart. Maintaining local injectivity means that we have to prevent each triangle from flipping its orientation or from degenerating to a point or a line. In terms of the singular values, that means that both have to stay strictly positive. And in continuous optimization, we can always add such inequality constraints using barrier functions. This means that we design our objectives such that whenever a singular value approaches 0, our objective diverges to infinity. And for the symmetric Dirichlet energy, this is already the case. So when one of these sigmas approaches 0, its inverse approaches infinity. So this energy already naturally acts as a barrier function. Many other objective functions, for example the popular as rigid as possible energy, do not have this barrier character built in. So there we need to explicitly add a barrier term if we want to maintain injectivity. And for completeness, we also have to add this case distinction here. So for a flipped or degenerate triangle, we don't even try to compute the singular values, but we just return infinity right away. Next, let's move from the plane-to-plane case to the surface-to-plane case. And really, not much changes here. The only difference is that the vertex positions of our source triangle now have 3D coordinates. But all we need to do is switch from a global 3D coordinate system to a local 2D coordinate system of the triangle's tangent space. The particular choice of coordinate system doesn't matter as long as we choose an orthonormal one, such that this change of basis doesn't change the shape of our triangle. And we do this for each triangle individually. And now we already have everything we need to formulate an optimization problem. So we want to minimize the integrated distortion measure, and our variables are the 2D vertex positions in the plane. So as we move vertices around, our objective changes, and we want to move them such that the objective strictly decreases. We usually also write all these vertex positions as a single variable vector x by just stacking all the u and v coordinates. So x has dimension 2 times the number of vertices. Now that gives us an alternative perspective to considering all these individual 2D points. Namely, we consider x as a single point in n-dimensional space. We also call Rn our search space or solution space. Every point in Rn corresponds to an arrangement of vertices in the plane, and we can evaluate the objective function for it. At many points it will be infinity, because our injectivity constraints might be violated. We call the set of points for which our constraints are fulfilled the feasible region. Because Rn is such a high-dimensional space, it will be practically impossible to exhaustively search it, or even to explicitly describe the feasible region. So again, we will stick to moving an initial feasible point through Rn. It is sometimes helpful to think of our search space as a height field, where we imagine all our n variable dimensions as a plane, or rather a hyperplane, and we add the objective as an additional dimension. Of course, we can only really visualize this for 2 dimensions, but as a mental picture, this might still be helpful. And this is also often called the optimization landscape, and we want to take a downward path through this landscape. We do this iteratively. So at the current point x, we always pick a descent direction d and then take a linear step into that direction. The most simple choice of update vector is the negative gradient of our objective, because locally this is the direction of steepest descent. And this is what it looks like in this example. So the length of the gradient itself doesn't naturally provide a very meaningful step size. If we take too big of a step, we could easily end up increasing the objective or even leaving the feasible region, like here where lots of triangles will flip. To prevent this, we need to scale our update by some factor s, and this factor is often found via a backtracking line search. Starting from an initial step size, we will repeatedly shrink it until we can guarantee a sufficient decrease in the objective. There are well-founded criteria for this decision, and a popular one is the so-called Amio condition. Now, with this gradient descent algorithm, we'd probably end up taking very tiny steps and we'd need an excessive number of iterations, like you can see here on the right. And this is because we essentially used a first-order approximation of the objective at every point, and this is often just not enough. We can really improve our steps by also using second-order information. So intuitively, what we do is we fit an n-dimensional paraboloid to our landscape that matches the slope and curvature at the current point. Now we compute the minimum of this quadratic approximation and use the vector pointing towards it as our update direction. On the right you can see this new direction and it looks a lot more promising. Now this method is called Newton's method, and when a few preconditions are fulfilled it even comes with nice convergence guarantees. Computationally, finding this direction, the Newton step, now amounts to solving a sparse linear system in each iteration. The system involves the gradient and the Hessian matrix of the objective at the current point. Now, computing these is often the biggest challenge when implementing Newton's method in practice. Luckily, we can compute the derivatives for each triangle individually and then combine the results. So a single triangle in the plane only depends on its 3 vertices. Each of these is a 2D point, and that makes 6 variables in total. So we compute a 6-dimensional gradient and a 6x6 Hessian matrix. Now for an arbitrary distortion measure, coming up with the right formulas for the gradient and Hessian might require some tedious derivations, but the derivatives of many popular measures can be found in the literature. An alternative to deriving the gradient and the Hessian manually is using automatic differentiation. So we can, for example, use tools that generate code for our derivatives, or we could use libraries that automatically compute derivatives at runtime. Now we are almost ready to run our optimization algorithm. There's just one more detail that we need to be aware of. The original Newton's method only works for convex functions. And one definition of convexity is that at each point in solution space, our quadratic approximation has a unique minimum. So here in 2 dimensions, it looks somewhat like this, but for example, not like this. Sadly, many popular objective functions, and that includes our symmetric Dirichlet energy, are non-convex. But we can adapt our algorithm to the situation by just projecting the Hessian matrix to a nearby positive definite one. To do this, we look at the eigendecomposition of the Hessian, and intuitively every eigenvalue that is negative corresponds to a direction in which our paraboloid bends downwards instead of upwards. And we need it to bend upwards in all directions to have a unique minimum. So what we do is we just clamp negative eigenvalues to a small positive number. Again, we can do this for each small per triangle matrix individually, and only then assemble them to the global Hessian matrix. And assembling the global n-dimensional derivatives is just a sum plus a little bit of index mapping due to different dimensions. So now, with this last detail in place, we can finally run our projected Newton's method on a surface-to-plane optimization problem. Projected Newton is a great general-purpose algorithm that can be used for many optimization tasks. But especially for surface-to-plane maps, there is a huge number of more specialized variants that sometimes outperform it by orders of magnitude. Many of these offer different replacements for the Hessian matrix, and they often encode more specific problem knowledge. Here we just list a few of these. In theory, we can replace the Hessian by any positive definite matrix, and we will still be guaranteed to get a descent direction. We will just end up taking a different path through solution space, potentially a better one, but potentially also a worse one. But now let's move on to the more challenging surface-to-surface case. As our first example, we will optimize a map via a planar intermediate domain. Now, how do we optimize map quality here? We already know how to optimize maps to the plane. So our first attempt could be to optimize both of these individually. In this example here, we initially see 2 input surfaces and their original wireframes, and now we compute and optimize 2 individual maps into the plane, overlay them, and use the resulting surface-to-surface map to swap their wireframes. Now, the result is not really what we wanted. There is a lot of distortion, and some of the fingers aren't aligned properly at all. But this is also not that surprising, because there's nothing that connects these 2 planar optimizations to each other. So if we have enough constraints available that align matching geometric features, then we might still obtain a relatively nice map, and a number of methods just do that. But if we want to automatically encourage this kind of alignment in the optimization itself, then we need to actually minimize surface-to-surface distortion, like in this example on the right. So here, think again of a little piece of surface A that experiences a lot of stretch when mapped to the plane. Now, if we map it from there to the target surface, and if it now experiences exactly the inverse type of stretch, then this is perfectly fine. There is no surface-to-surface distortion. It's okay if there is a lot of distortion in the intermediate plane, as long as this cancels out between both maps. Now, how do we do this in a discrete setting? For a triangle of A, the Jacobian JA lets us measure its distortion to the plane. For a triangle of B, we have the Jacobian JB. We can compose one with the inverse of the other, so we get the Jacobian J for the surface-to-surface map. But now we have a problem with our discretization. The Jacobian of A is constant per triangle of A, and the Jacobian of B is constant per triangle of B, but the composed Jacobian is only constant in the area where the two triangles overlap in the plane. So we actually have to intersect both triangulations with each other in the plane and compute all of these intersection polygons. The result is an overlay mesh, as we've already seen in the representation chapter. But this includes computing all these intersection vertices between edges. And it turns out that we even have to compute these in a differentiable way. And why becomes more clear when we actually write down a distortion measure. So here again, the symmetric Dirichlet energy as an example. So it's a sum over all overlay polygons. We measure stretch in both map directions via the surface-to-surface Jacobian. We can also write that in terms of the individual Jacobians, as seen before. And now this is a pointwise measure that needs to be multiplied by an area. So we compute the area of our polygon in the plane. But since we actually want to integrate over the input surfaces, we lift this area, once to mesh A and once to mesh B. And we can do this via these extra terms, again based on the map Jacobians. And this is already the distortion measure we're looking for. This time our variables are the vertex positions of both meshes in the plane. But now we realize that not only all these Jacobians depend on these variables, but also the area weight, which means that we have to compute derivatives of it, and that also involves computing derivatives of all these intersection points. So especially in this quite complex scenario, automatic differentiation is an extremely valuable tool. Okay, but now we can run the projected Newton's method we've seen before, just in this slightly more complicated setting where the main difference is that we have to compute all these overlay polygons each time we evaluate the objective function. And that is, but in particular, in each step of the line search. Here's an example where we see such an optimization method in action. This is visualized via texture transfer. Back in chapter 1, we also introduced map representations that are not via the Euclidean plane, but via the sphere or the hyperbolic plane, either represented in global coordinates or via spherical or hyperbolic metrics. In any case, we were always able to turn these map representations into an explicit piecewise linear form, an overlay mesh, or simply a set of overlay triangles, and their embedding on both surfaces. Now, as soon as we have such a set of linear pieces, we can always just compute the map Jacobian per piece and evaluate a surface-to-surface distortion measure. So here things don't actually get that much more complicated. The only big caveat is differentiability. Think of the chain of all the computations that we perform. We start with our variables, for example, vertex positions in some intermediate domain. Based on these, we establish the formulas needed to map points from A to B, and this might require interpolating on the sphere or in the hyperbolic plane. Then we turn this pointwise map into an explicit piecewise linear form, Then we compute the Jacobians and area terms, and then finally we plug these into a distortion measure. So there's a lot going on here, and the big task is to design all these steps such that they are differentiable, meaning that we can compute the derivatives of our final distortion measure at the end of this chain with respect to the variables at the very beginning of this chain. The formulation via the plane that we just looked at in detail is one example of how to do this, but these differentiability aspects require us to be quite careful when designing a map representation, and different ways of doing this are definitely still subject to ongoing research. And finally, here's an example of a map optimization via a hyperbolic metric. So let's watch this again now with a distortion heat map. Now let us end this map optimization chapter with one final remark. In this lecture we focused our attention purely on optimizing intrinsic map distortion, but there are also aspects that cannot be captured intrinsically at all. Generally speaking, intrinsic measures are unable to see mean curvature, for example ridges in our input geometry, because simply bending a surface doesn't have to induce any stretching. Like here, where both of these maps have zero intrinsic distortion, but we would probably prefer the first one. For this, there are also extrinsic distortion measures, for example in elastic bending energy, and these do capture such aspects. Finally, besides bending and stretching, it would also be worthwhile to integrate more semantic information. And this could come in form of shape descriptors that more accurately identify corresponding points, or via data-driven approaches trying to infer semantics from a large number of input examples, and so on. So all of these are exciting related topics, and they're still being heavily researched.
Alright, we have now seen how maps, in particular maps between surfaces, and in particular maps that are homeomorphisms, can be represented, initially constructed, and optimized, so as to serve as valuable high-quality ingredient or foundation for a variety of geometry processing applications. Along the way, we have seen that there are some parts for which simple and/or elegant solutions have been found already, and some parts for which known solutions still leave room for improvement and things to be desired. Let us briefly summarize these here to conclude, so as to perhaps leave you with some inspiration for directions to think about. When we considered the task of map initialization, we have seen that it is important to make sure that already the initial map has the desired topology, the desired homotopy. Such choices are mostly done greedily with some recent non-greedy advances, but there is definitely a lot of room to make the initialization stage more homotopy aware. Alternatively, it could be quite interesting to look into ways to perform the map optimization, not in a continuous deformation manner like we discussed here, but to be more flexible, to also allow the optimization to switch map homotopy classes. This, however, inevitably adds a combinatorial component to the optimization problem, making it significantly more challenging. Without some very clever special purpose strategies, this will likely be far from practically feasible. On a related note, because continuous optimization commonly allows us to find a local optimum only, it is not only the initialization's topology that matters. The initial state has an effect on the result beyond just topology. Making better informed decisions, for instance using better informed correspondences and landmarks, could help quality in the end. The ultimate goal in most cases would be to operate not just geometrically, but to automatically take semantics into account to quickly get the correct or the desired map. And there are various directions, from classical data-driven approaches to modern convolutional machine learning techniques that have the potential to make beneficial contributions in that regard in the not too distant future.
In terms of continuous map optimization, the surface-to-plane case has received quite some attention recently, in particular when it comes to speeding it up, for example via specialized preconditioners and other strategies. Unfortunately, many of these advances don't trivially extend to the surface-to-surface case, because there is some added complexity. For example, the varying combinatorial structure of the overlay mesh, or the non-existence of a global coordinate system in some representations. Also, the optimization landscape may be of lower smoothness. In some cases it's just C0 continuous instead of C1 continuous. This and other aspects cause additional challenges that are specific to maps between surfaces and not so relevant when just mapping to the plane. Finally, robustness, in particular numerical robustness, plays quite a big role in surface mapping. In particular, when an initial map has extremely high distortion, it can easily happen that optimization methods fail at some point. This is usually due to numerical inaccuracies, even if the map is formally valid. There has been recent progress towards improving this, but mostly in the initialization phase, and in our opinion it would make sense to continue this research also with focus on the optimization phase. The surface-to-surface case adds further challenges. For example, overlay meshes need to be computed and differentiated consistently, even in nearly degenerate configurations. And especially the spherical and hyperbolic spaces add even more numerical difficulties to this. So for many such cases, solutions that succeed, not only commonly but also provably, have yet to be found.
Well, and this concludes our lecture. Thanks for your attention.
Thank you.
And see you soon.